Introduction to Quantum Information Processing. We are now starting Part 3 of the course, Quantum Information Theory. This part consists of several loosely connected topics that fall under the umbrella of quantum information theory, and they include the density matrix formalism, distance measures between states, entropy and noiseless coding, quantum error correcting codes, and a little bit of fault tolerance, and the theory of non-locality. Welcome to Lecture 14, Quantum States as Density Matrices. To begin with, let's consider the following scenario. Suppose that Bob wants a plus state from Alice. So suppose that Alice has the apparatus that enables her to set states, and Bob doesn't, so he wants Alice to create the state for him and send it over to him. But suppose that Alice's state preparation device is broken. Suppose it can only prepare computational basis states ket 0 and ket 1. Well, Alice could simply inform Bob that her device is broken so she can't do what she wants, but suppose that Alice decides instead to fake it. Suppose she tries to fake it by sending this fake plus state. What she does is she flips a coin, and with probability half she sends Bob the ket 0 state, and with probability half she sends Bob the ket 1 state. And this is the state that Bob actually wants, the equally weighted superposition of 0 and 1. The question is whether Bob can tell the difference between these two states. If what Bob does is he measures the state in the computational basis, then everything is fine. In both cases, the outcome will be 0 with probability half and 1 with probability half. But what if Bob does something else? Please feel free to pause and think about this. Yes, Bob can tell the difference. For example, if Bob applies a Hadamard transform and then measures in the computational basis, then it's easy to see that the distribution of outcomes will be different in the two cases. Okay, now let's consider a different scenario. Suppose that now what Bob actually wants is a fake plus state from Alice. So he actually wants Alice to create ket 0 with probability half and ket 1 with probability half and send it over to him. But suppose that Alice's state preparation device is broken in a different way. Suppose that Alice can only prepare ket plus states and ket minus states, that she can't prepare computational basis states. What can Alice do? Well, she could try sending Bob a true plus state, but that won't work because we already saw that the two states are distinguishable. What if Alice tries to fake it instead by sending this state, that I'll call the plus-minus state? With probability half, she sends ket plus, and with probability half, she sends ket minus. Can Bob tell the difference between this plus-minus state and a fake plus state? In other words, is the plus-minus state a good fake plus state? Please feel free to pause and think about this. It might surprise you, but actually Bob can't tell the difference. Even though the states are not identical in terms of the preparation procedure, there's no procedure that Bob can perform that will detect any difference. We are now in the realm of probabilistic mixtures of states. So this is a concept that makes sense, where you could use a classical random process to decide which state vector to prepare. So we call this a mixed state, and in general it's of this form, where we have a probability distribution, probabilities p1 up to pm, and for each case we have a state, and depending on the sample that we get from the probability distribution, we construct the corresponding state. So with probability p2, we generate psi2, and so on. And let me point out that the states need not be orthogonal, and in fact the number of states need not correspond to the dimension of the system. Now, the more ordinary states that we've been discussing up until now in the course, where you have a single vector state, we'll call those pure states. Here are some examples of mixed states. Well, the examples we just saw are the case where with equal probability we choose ket 0 or ket 1, And another mixed state is where with equal probability we choose ket plus and ket minus. I claim that those two mixed states are indistinguishable, but I didn't really explain why. Here's another mixed state. With equal probability we choose either the ket zero state or the ket plus state. Notice that these two states are not orthogonal. Here's a degenerate case of a mixed state where one possibility occurs with probability 1 and there are no other possibilities. And here's an example of a mixed state with 4 possibilities. Even though it's a qubit, a two-dimensional system, there are 4 different 1-qubit states and each has a probability associated with it. That makes sense also as a mixed state. And here's another example of a state where I guess the key observation is that the probabilities need not be equal. The first probability is around 85%, and the second probability is around 15%. These are all mixed states. Here's a question. Which of these are indistinguishable? So some of them are different, but some of them are, even though they're not operationally the same in terms of the construction procedure, if we were to play the Guess My State game where I produced either the first state or the second state from a set of 2 of these states, you couldn't tell the difference. In order to understand these states better, we can express them in terms of density matrices. First of all, the density matrix of a pure state, a vector state, is just the state times its conjugate transpose. So if the state is ket psi, then the density matrix is ket psi bra psi. For example, if we have a 1-qubit system with amplitudes alpha 0 and alpha 1, then the state looks like this. We have the state vector alpha 0 alpha 1 and its conjugate transpose alpha 0 conjugate alpha 1 conjugate. And we multiply the column vector times the row vector and we get a 2x2 matrix. And the diagonal terms are these amplitudes squared, and the off-diagonal terms are kind of the cross terms of the amplitudes. Okay, so that's how we define the density matrix of a pure state. And we can also define the density matrix of a mixed state. Here's a mixed state where we have a sequence of vectors and corresponding probabilities. And the definition of the density matrix is we take the weighted average of the pure state density matrices. Okay, so the sum is expanded here. Let's look at some examples of density matrices. So for ket 0, it's this. So it's a 2x2 matrix with a 1 in the top left corner. And for ket 1, it works out to a 2x2 matrix with a 1 in the bottom right corner. In general, for computational basis states, the density matrix will be a diagonal matrix with a 1 in one position. Okay, the plus state. Well, here's the expression for it, and we end up with this 2x2 matrix with 1/2 in each entry. The ket minus state. Well, it's a similar matrix, except in the off-diagonal entries we have -1/2. Okay, what about mixtures? So if we take an equally weighted mixture of ket 0 and ket 1, then we take the average of those two density matrix, and we end up with this diagonal matrix with 1/2, 1/2 along the diagonal. What's the density matrix of the equally weighted mixture of ket plus and ket minus? Well, we take the average of 2 different matrices than the case just above this, but the average works out to the same matrix. It's again a 2x2 matrix that's diagonal with 1/2 along the diagonal. The fact that the density matrices are the same is related to the fact that the 2 probabilistic mixtures are indistinguishable. Okay, we could work out the density matrix of this state, an equally weighted mixture of ket 0 and ket plus, but I'm going to leave that as an exercise for you to work out. It's quite easy. Let me make a comment about global phases. Remember, when we represent states as vectors, there's this issue that if you have a vector state and you multiply it by a unit complex number, a number of the form e to the I theta, where theta is a real parameter, then it's essentially the same state. It's indistinguishable from the original state. If we compute the density matrix of this state, then we're going to end up with the e to the I theta as a scalar multiple and also e to the minus I theta when we take the complex conjugate, which cancel out, so we get the original state. So what this means is that we don't have this issue where we have to take equivalence classes of density matrices. You get exactly the same density matrix if you multiply a state by a phase, a global phase. So that's nice. Here's some more examples of density matrices involving higher dimension than 2. So if you have a 2-qubit system, this computational basis state, it's a diagonal matrix with a 1 in one entry. What about this Bell state? Well, we plug it into the expression, and it's the 4x4 matrix with these 1/2 entries in the corners. What about this mixture of ket 0, 0 and ket 1, 1? Think of that as a fake Bell state. You get a different density matrix. You have the 1/2 along the diagonal, but you don't have the 1/2 in the corner. Now I'd like to consider what happens if we apply a unitary operation on one of these states. So we have a state like this, which is a probabilistic mixture of pure states, and it has a density matrix, and we receive that state, and then we apply a unitary operation. What is the new density matrix going to be? Well, after we apply the unitary U, we now have a probabilistic mixture of the same vectors, but each one is multiplied by the operator U. So if the initial state we receive psi I, then when we multiply by U, we have U times psi I. Because remember, what we actually get is one of those states once we sample the probability distribution. So that's the mixed state after applying the unitary. And now we plug it into the formula for the density matrix, and we get this expression. And notice on the right side, we've used the fact that the conjugate transpose of U psi k is the bra of psi k times U star. And what's nice about this expression is we can factor out the U on the left side and the U star on the right side. And if you look at what's inside the parentheses, that's just the expression for the original density matrix. So if we want to apply U to a state with density matrix rho, then the outcome doesn't depend on how rho was constructed. It doesn't depend on the specific probabilistic mixture that was used to obtain rho. It just depends on the density matrix itself. Now let's consider the related question of what happens if you perform a measurement on a state with a density matrix of rho. So suppose this is the initial state. It's some probabilistic mixture of pure states, and there is its density matrix. And now we perform a measurement in the computational basis. Let's suppose it's a d-dimensional system, so there are d computational basis states, and we'll number them from 0 to d-1. What's the probability of outcome k? This probability will now depend on two sources of randomness. One source of randomness is the random process that was used to generate the state, the sampling of the probability distribution, and the other source of randomness is the randomness arises in the definition of measuring a pure state. So if the actual state that you received happened to be psi I, conditional on the state being psi I, the probability of outcome k is the absolute value of the projection squared of that state on the computational basis state, ket k. So it's this expression here. And this expression is equivalent to the inner product of k and psi I times the same inner product but in the opposite order. Because if you compute the same inner product in the opposite order, you have the conjugate of the original number, and any number times its conjugate is the absolute value of the number squared. Now, let me make a comment about this expression on the bottom of this slide. We have some bras, and those are row vectors, and some kets, and those are column vectors. And one way to parse this expression is to think, well, we're taking an inner product, we're multiplying the first two guys, we're multiplying a row vector times a column vector, and that gives us a scalar. And then we're multiplying again a row vector times a column vector and getting another scalar, and then we're taking the product of those two. But really what we're doing is we're multiplying four matrices together. Some are row matrices and some are column matrices. And matrix multiplication is associative, meaning we can move around the parentheses. So this expression is equivalent to the expression where we first multiply the inner two ket and bra in order to get a square matrix, and then we take that square matrix and we multiply by the bra on the left side and the ket on the right side. It's useful to bear in mind that this kind of calculation maneuver is sometimes useful. Now, getting back to the measurement problem, If we want to find out what's the actual outcome for the mixed state, then we want to take all the conditional probabilities of outcome k given that the state is psi I averaged over the probabilities that the state is psi I. So it's this averaging expression here. And if you look at this expression, you can factor out the bra k and the ket k on the left and right side respectively. And what's inside the parentheses? That's just the expression for the original density matrix. So the probability of outcome k depends only on the density matrix rho, and it doesn't depend on the probabilistic mixture that was used to generate it. So in summary, if we apply a unitary operation or a measurement on a mixed state with density matrix rho, then the outcome can be calculated just by knowing what rho is, without making any reference to the probabilistic mixture that generated the state. It follows from that any two states with the same density matrix, even if they were generated by different probabilistic mixtures, are operationally indistinguishable. Well, there's a loose end here, because I haven't really captured everything you can do with a state. I haven't really addressed the issue of exotic measurements. Remember exotic measurements that were introduced in Lecture 3? Those are measurements where you add an ancilla qubit, and then you perform a unitary operation in a higher dimensional space, and then you perform a measurement. It turns out that the basic result holds even for these exotic measurements, but we'll prove this later when it's more convenient for us. Now, not all square matrices are density matrices of quantum systems. There are certain properties that characterize which square matrices are density matrices. And the theorem is the following, that if you have a d by d matrix, it's a valid density matrix if and only if it satisfies three properties. 1, the matrix is Hermitian, meaning that it's equal to its conjugate transpose. 2, the matrix is positive, which means that for any vector state, if you multiply by the bra of that state on the left side and the ket of that state on the right side, you get a quantity that's greater than or equal to 0. And the third property is that the trace of the density matrix is 1. And what's the trace of a matrix? The trace is the sum of the elements along the diagonal of the matrix. So every density matrix has these three properties, and any matrix you can write down that has these three properties corresponds to the density matrix of some mixed state. I'm not going to prove this. It's not that difficult, but I'll leave it as an exercise. I'm going to state another theorem that's also useful to keep in mind, which is that among all the density matrices, some of them correspond to pure states. So in other words, the case where one pure state occurs with probability 1 and all the other cases occur with probability 0. And that's the case if and only if the trace of rho squared is equal to 1. And that's also not that difficult to prove, but I'm not going to get into it here. I'll leave it as an exercise. Now, I'd like to review various properties of matrices and the trace function that I've just made reference to for clarity. Up until now, we've mostly dealt with unitary matrices, but now we're dealing with matrices that are not necessarily unitary. Define a square matrix to be normal if the matrix M has the property that M star and M commute, that M star M is equal to M star. Now this is a kind of abstract definition, and that's often the definition you see in textbooks, but a matrix is normal if and only if it can be expressed in this form. It's normal if and only if it's a diagonal matrix conjugated by a unitary matrix. And what that means is that the matrix has the property that there exists an orthonormal basis such that if you represent the matrix in the coordinate system of that orthonormal basis, then the matrix is diagonal. And this is called the spectral theorem. And since a matrix is normal if and only if it has this property, you could actually take either of these as a definition of normal, because one implies the other. For perspective, let's look at some matrices that are not normal, which I'll call abnormal. So there are some matrices that, as you know, are not even diagonalizable, and those can't be normal. And there are matrices that are diagonalizable, but for which the eigenvectors are not orthogonal, and those are also not normal. The eigenvectors of distinct eigenvalues have to be orthogonal. It's useful to have this picture in the back of your mind that in the coordinate system, with respect to some orthonormal basis, a normal matrix is diagonal. And then all unitary matrices have the property that the eigenvalues are unit complex numbers, that they're on the unit circle in the complex plane. And a matrix is Hermitian if all the eigenvalues are real numbers. And a matrix is positive if all the eigenvalues are real and they're greater than or equal to 0. And sometimes this condition is called positive semidefinite, but we're going to follow the mathematical convention of just calling this positive. Another property that holds is that the trace of a normal matrix is the sum of its eigenvalues. Maybe now is a good time to review some basic properties of the trace function. The trace is defined for square matrices, and it's very easy to define it. It's just the sum of the diagonal entries of the matrix. And it has some nice properties. It's linear, of course. The trace of A plus B is equal to the trace of A plus the trace of B. And also, it holds that the trace of A times B is the trace of B times A. And this implies that the trace is coordinate system independent, because if you conjugate A by some S, if you left multiply by S inverse and right multiply by S, where S is some invertible matrix, then the trace doesn't change. And also I'd like to point out that A and B need not be square matrices for the trace to make sense, as long as the product of the matrices is square. So if you have a column vector times a row vector, those aren't square matrices, but the product can be square, and then the trace makes sense. So the trace, if the dimensions are the same, the trace of ket, psi, bra, phi makes sense, and it's also equal to the trace of the two vectors in the opposite order, which is the inner product of the two vectors, which is a scalar. A word of caution. Here are some properties that in general the trace function does not have. In general, the trace is not like the determinant. It's not multiplicative, that the trace of a product is not the product of the traces. And moreover, although the trace of AB is the trace of BA, it doesn't mean you can reorder the arguments arbitrarily. The trace of ABC is not equal to the trace of ACB in general. What you can do, though, is you can cyclically permute the argument of the trace, and then it will be invariant. The final topic for this lecture is the Bloch sphere, which is a very nice way of thinking about qubits. The set of all 2 by 2 density matrices, so density matrices of qubits, has a very nice representation as a linear combination of the Pauli matrices. So here are the 3 Pauli matrices, and I've added the identity matrix as an honorary Pauli matrix. And every 2 by 2 matrix is some linear combination of those 4 matrices. We can express a density matrix as a linear combination of those 4. And notice that since the trace of Pauli X, Pauli Z, and Pauli Y are all 0, if the trace of the density matrix is 1, the only way that can be is if the coefficient of the identity is 1/2. So the coefficient of the identity term has to be 1/2, and what's left are the coefficients of the other 3 terms that can vary, and it's convenient to write it in this manner where we've divided the whole thing by 2. Let's develop a geometric picture for the set of all triples of coefficients, C sub x, C sub y, and C sub z, that correspond to valid density matrices. So let's start with pure states. Any pure state can be written in this form with 2 real parameters, 2 angles, theta and phi. And if you plug that into the formula for the density matrix, we get this matrix. And we can rewrite this matrix in a slightly simpler form like this. And what I've done here is I've just used some high school geometric identities. So for example, the sine of twice times an angle is equal to the cos of the angle times the sine of the angle. And also there's a trigonometric identity that the cos squared of an angle is equal to 1 plus the cos of the angle, all divided by 2. Okay, so this matrix on the bottom right of the slide is the general form of the density matrix of a pure state. Let's study this matrix a little bit further. So I can write the matrix in this manner, and I've done something very simple. E to the I phi is just equal to cos phi plus I sine phi. So I've expanded it a little bit. And in this expanded form, we can actually see what the coefficients are of the three polys. For example, the coefficient of the poly z is cos theta. Why is that the case? Because if you look along the diagonal, you have a plus cos theta and a minus cos theta. And with a little bit of, just staring at things, you can tease out where these other coefficients came from this matrix. Okay, so those are the Cx, Cy, Cz coefficients for pure states. So those are all states of this form where we have these expressions in terms of cos and sine of angles phi and theta. Now this expression is actually the expression for the polar coordinates of points on a sphere. So here's a picture of a sphere in 3 dimensions with the x, y, and z axis. And think of the Earth. So we have the North Pole on top, and the coordinate system can be expressed in terms of a latitude and a longitude. And the latitude is the angular distance away from the North Pole. The longitude is the east-west distance from some arbitrary starting point, which is maybe the international dateline, and that would be 0, and what the angle is away from that. And those two parameters, theta and phi, can specify any point on the surface of the sphere. Okay, so all the pure states correspond to points on the surface of the sphere. Where does ket 0 lie? Well, ket 0 is in the North Pole, and ket 1 is in the South Pole. Notice that these are orthogonal vectors, but if we represent the density matrices as points on the Bloch sphere, then they're antipodal. In other words, the angle is 180 degrees rather than 90 degrees between them. What about the ket plus state and the ket minus state? Well, those lie on the equator. The ket plus state is right where the international dateline intersects the equator, and the ket minus state is the point on the opposite end of the sphere. And notice again we have this angle doubling. For example, the angle between the vector ket 0 and ket plus is 45 degrees, but on the Bloch sphere the angle is double that. The angle is 90 degrees. Now, there are 2 other points on the equator that are kind of natural to consider, which are the points that on the Bloch sphere are 90 degrees away from ket plus, ket minus, ket 0, and ket 1. And those are actually points that we'll call ket plus I and ket minus I, which are defined as follows. So there's some nice symmetry among those 6 different states. So the surface of the Bloch sphere consists of all the pure states, and it turns out that the mixed states are in the interior of the Bloch sphere. If you have a probabilistic mixture of pure states, then you just take the weighted average of those points on the surface, and that gives you a point in the interior. So if you take an equally weighted average of ket 0 and ket plus, you get a point right in the middle of the Bloch sphere, and that corresponds to the density operator of the state that you get if you randomly choose either ket 0 or ket 1. So in the case of qubit systems, it's sometimes very useful to think of them as points on the surface or in the interior of the Bloch sphere, and think of the operations being performed on the Bloch sphere. A word of caution. This works for qubits, But for higher dimensional systems, there is no longer a sphere. There's some geometric shape, but it's not spherical, and it doesn't have properties that you might think are natural. For example, that all the pure states are on the surface. Okay, let's end the lecture now.